Hello friends. Here is something that stops most calculus students cold. A function can be perfectly continuous, no breaks, no jumps, no holes anywhere on its graph, and yet have no well-defined slope at any single point. Not one. That sounds impossible, but it is completely true, and it reveals that continuity and differentiability are two distinct mathematical ideas, not just two ways of saying the same thing. Understanding that difference is the whole point of this video. In this video, we are going to define both concepts precisely, unpack the one-way relationship between them, and look at concrete examples that make the difference crystal clear. Let's start by pinning down exactly what continuity means. Continuity is the idea that a function has no interruptions. Intuitively, you can trace the graph without lifting your pencil, but the formal definition is what gives that intuition real power. A function f is continuous at a point x equals a when three conditions hold. First, f of a is actually defined. Second, the limit of f of x as x approaches a exists. Third, and most importantly, that limit equals f of a. The function value and the limit value must agree. If there is a hole, a jump, or a vertical break at a, at least one of those three conditions fails. Continuity is a local property. A function can be continuous at some points and discontinuous at others. Now let's build on this and define what it means for a function to be differentiable. Differentiability is a stricter idea. A function is differentiable at a point x equals a if it has a well-defined tangent line there, meaning a unique finite slope. We measure that slope using the difference quotient. Take the slope of the secant line connecting x equals a to a nearby point x equals a plus h, then let h shrink towards 0. If that limit exists and is finite, the function is differentiable at a, and the limit value is the derivative f prime of a. Geometrically, this means the curve approaches the same straight line from both the left and the right at that point. No sharp corners, no vertical tangents, no abrupt kinks allowed. And as we are about to see, differentiability actually guarantees continuity, making it the stronger of the two conditions. That relationship is exactly what the next slide is about. Here is the central fact you need to lock in. Differentiability implies continuity. If a function is differentiable at a point, it must be continuous there. The logic is straightforward. If the difference quotient limit exists, then as h goes to 0, f of a plus h must approach f of a, which is exactly the definition of continuity. So differentiable is the stronger condition. But the reverse is not true. Continuity does not imply differentiability. A function can be perfectly continuous at a point, and still fail to have a well-defined slope there. Think of it as a one-way door. Differentiable gets you continuous for free, but continuous tells you nothing about differentiability. This asymmetry is what makes the next slide so important. We need to see exactly where continuity holds, but differentiability breaks down. Let's look at two concrete cases. First, the absolute value function, f of x, equals the absolute value of x. This function is continuous everywhere, including at x equals 0. But at that corner, the slope coming from the left is -1, and the slope coming from the right is +1. Those one-sided limits of the difference quotient disagree, so the overall limit does not exist. No derivative at x equals 0. Second, f of x equals x to the power of 2/3. Again, continuous everywhere. But at x equals 0, the tangent line becomes vertical, meaning the slope grows without bound. An infinite slope is not a well-defined finite derivative. Both cases are continuous, neither is differentiable at the origin. These are not edge cases. They show the typical ways differentiability can fail while continuity holds. Up next, we bring every piece together into the final picture. Let's bring it all together. Every differentiable function is continuous, but not every continuous function is differentiable. Differentiable is the stricter condition. It demands smoothness, a unique well-defined slope, not just the absence of breaks. Continuity is the floor. Differentiability is a higher bar. The mental model to carry with you is this. When you encounter a function, ask first whether it is continuous, and only then whether it is smooth enough to have a derivative at each point. Corners, cusps, and vertical tangents all mark places where continuity survives, but differentiability fails. If you remember just one rule from this video, let it be this. Differentiability implies continuity, but the reverse is never guaranteed. Thanks for watching, and we will see you in the next one.